What's up, Logic fans? It's Ash again. We're going to be covering section 1.2 of the text today, and in this section we discuss a very important assumption for the entire course, known as the Law of Bivalence. Let's jam. Okay, so every course that you take has to make some assumptions in order to get started, and our assumption for our course is the law of bivalence. Now, there are logics which go beyond the law of bivalence, for example, multi-valued logics. These are beyond our scope. What the textbook in this course is offering you is an introduction to sort of classical logic, or what we might call classical logic. So, in classical logic, we make the assumption of the law of bivalence, okay? And bi meaning two, and valence meaning two-valued logic. So the basic idea is fairly simple, okay? We assume that there are exactly two truth values, true and false, okay? And that's it. And as I noted, there are logics which sort of go beyond this, but for introductory purposes, this is what we're going to be working with, okay? Throughout the entire semester and throughout the entire course. So there are exactly two truth values, and they are true and false, all right? Now, the law of bivalence basically consists of these three fundamental assumptions, right? So it's sort of all of them together. But let's go through them one by one. So one part of the law of bivalence is what we call the law of excluded middle, which we're going to abbreviate LEM throughout the entire course and throughout the entire, all of these videos and throughout the textbook, Bivalent Logic Explained. So the law of the excluded middle asserts that every proposition, okay, pick a proposition out of a hat, it has at least one truth value. That is to say, the proposition you picked out cannot have no truth value whatsoever. It has to have at least one of the truth values, true and false, okay? It's got at least one of those. Similarly, we have the law of non-contradiction, and the law of non-contradiction has a very sort of distinguished history in philosophy and mathematics, computer science as well, and it's sort of it's a law that philosophers posit as sort of a fundamental law of thought. Okay, we're going to talk about another one when we get into chapter 6 and we talk about the reflexivity of identity, that everything is identical with itself. But this is a really bedrock sort of principle of philosophical reasoning, okay? The law of non-contradiction, and it asserts that every proposition has at most one truth value. That is to say, it cannot be both true and false. Pick a proposition out of a hat. That proposition you picked out, it cannot be both true and false. Now, it's really important for you to note that these assumptions do not require us to know the truth value of the proposition in question. So you pick a proposition out of a hat, it might be true that you and I don't know what the truth value of it is. But under the law of bivalence, we know, and this is our assumption, right, that it is either true or false, and it's going to be at least one of those, and it's going to be at most one of those. In other words, it's going to have one of those two truth values, and it's not going to have both of them. So it's going to be true or false, not neither, and not both is the idea. So the law of bivalence is just both of those together, and when you combine the at least one and the at most one, you end up with exactly one. Every proposition has exactly one truth value, true or false, regardless if we know the truth value of the proposition in question that holds. Okay, and what I really want to do here is I want to pause for the rest of this video, and I want to take stock of these terms, at least one, at most one, and exactly one. Because this is a really good time to get these terms down right now, okay? These terms are going to be so important as sort of background working concepts for all of our work in logic, regardless of what textbook you're using, that it really behooves you to take a minute and really understand these. So let's go ahead and do that now. Okay, so let's get this down, and we're going to start with the concept of at least, okay? Now, this might be a little painstaking, but it's super important for our future work, so let's make sure we're all super clear on this. At least n. Suppose the following sentence is true. Jack has at least 3 sisters. Okay? Now, we're just going to take it as a given that that's true. Draw a number line indicating the possible number of sisters Jack has. Be sure to clearly indicate which possibilities are ruled out and which possibilities are ruled in. So you're assuming this is true, and I've got you started here with your number line. And I want you to indicate which possibilities are ruled in and which possibilities are ruled out, provided that this statement is true. So pause now and see if you can figure that out, and we'll come back together and do it together. Okay, so hopefully you've had a chance to do this, but, if he has at least 3 sisters, it's impossible that he has, 0 sisters, that he has, let's say, exactly 0. It's impossible that he has exactly 1. It's impossible that he has exactly 2, but it is possible that he has exactly 3. Okay, so I'm reading this as exactly. That was a little ambiguous, but yeah, so this, filled in circle is supposed to indicate that this is a live possibility. He has exactly 3. It's also possible that, he has exactly 4, or he has exactly 5, or he has exactly 6, and anything greater than that, right? So none of this stuff is ruled out by the statement Jack has at least 3 sisters, but all of this stuff is ruled out by the statement Jack has at least 3 sisters. That's supposed to be the point, okay? And analogously, right, the law of excluded middle, so let's get that back up on the board here so you can see it. The law of excluded middle asserts that every proposition has at least one truth value. So following our model for at least, can you, fill in this number line, what's ruled in and what's ruled out given the truth of this statement? Pause now. Okay, so in this case, it's at least 1. So n is 1 as opposed to 3 in this particular case. So, you pick a proposition out of a hat, and it's guaranteed to have at least 1, and it doesn't rule out any of these. The law of excluded middle doesn't rule out the possibility of a proposition having 2, 3, 4, or 5. None of that's ruled out. But this is ruled out, the possibility of it's having none, right? It has to have at least 1. So in this case, that's what's ruled out there. Okay, let's turn our attention to the at most 1 clause. So for at most n, right, this other clause, right, let's do an example and make sure we're absolutely 100% clear on its, strict mathematical meaning. So in this case, we'll say Jack has at most 3 sisters. Now, using a number line, can you tell me what's ruled in and what's ruled out, supposing this statement is true? Pause now. All right, hopefully you've had a chance to try it, but yeah, if it's true that he has at most 3 sisters, then that includes the possibility that he has exactly 3, so that's included. It's also possible that he's got exactly 2, and that, if he has exactly true, it's true that he has at most 3, right? So this is working as an upper bound, we might say, whereas the whereas the at least clause works as a lower bound, all right? It's possible that he has at exactly 1, right? If he has at most 3, that's a possibility. It's also possible, this is ruled in, this is possible, okay, so this is absolutely possible, that he has none, right? If he has no sisters, it's true that he has at most 3. 3 is again an upper bound, right? Now it's not a least upper bound, but it is an upper bound, okay? So let's go ahead and do this analogously with the law of non-contradiction. So recall that the law of non-contradiction, LNC, asserts that every proposition has at most 1 truth value. So on analogy with this at most clause, what's ruled in and what's ruled out by the law of non-contradictions at most 1 assertion. Pause now. Okay, and hopefully you had a chance to figure this out, right? But, at most 1 just means that it's either, it's between 0 and 1. So it doesn't rule out the possibility of none, right? That's included, right? So if every proposition has at most 1, that's consistent with, from a purely logical point of view, with the possibility that a given proposition has none. So, it would be drawn this way, and of course all of this is ruled out, just as all of this was ruled out as well, and 4 was ruled out too, right? Okay, so this is interesting. And now, we can talk about the law of bivalence, and the law of bivalence is interesting because the law of bivalence, right, I'll just abbreviate that LB, was, both the law of excluded middle and the law of non-contradiction together, and it was every proposition has exactly one truth value. So let's go ahead and do an example focusing on this exactly clause. So here let's talk about, exactly n. In this case, in our example, it'll be exactly 3, just as an example, okay? But recall, our previous 2 graphs, this was when Jack had at least 3. This was all ruled in, this was all ruled out. At most 3, this was all ruled out. These possibilities were all ruled in, okay? Now, basically, combine the graphs because exactly 3 is both at least 3 and at most 3. All right, so in other words, how would you fill in the graph here for this statement, assuming that it's true? Pause now. All right, so there's only one way to make them both true, right? The only things that sort of coincide here is this case. So in other words, exactly 3 rules in this case and rules out every other possible case. Okay, so that's basically what happens when you combine them. Let's go ahead and do the same thing just so we're 100% clear on the law of bivalence. Let me set it up for you. So by analogy here, right, our law of excluded middle is that the at least one case, every proposition, any old proposition you pick out of a hat has at least one truth value. So that includes the possibility of 1, but it also includes these other possibilities. The only thing it really excludes, right, is, the only thing it really excludes is 0. So again, this is like a lower bound, right? A least bound, and so it excludes anything before it, prior to it, right? And this is an upper bound, right? The law of non-contradiction. Every proposition has at most one truth value, so that says it can have this many and anything less than that or fewer than that. But and so it's only excluding all of this stuff to the right. Now. If we combine the two, how do you make them both true? Suppose that the law of bivalence is true. Every proposition has exactly one truth value. How would you fill it in this case? Pause now. All right, hopefully you've got it. But, the only thing that's possible is that, the one case. Everything else is ruled out. Okay. So, again, we can summarize the result here this way. At least n can be mathematically, defined as, between n, possibly identical with n, and infinity, right? And that's what we saw in our graphs. Similarly, at most n can be mathematically defined as between 0 and n, anything between 0 and n, including 0 and including n itself. And of course, in the case of exactly n, you end up with x just is n, and whenever you have at least n and at most n, when n is equal in both cases, that's exactly n, right? So that's how all of that combined. Now, interestingly, you can also try to do some combinations where you have, let's say, at least n and at most m, where n is not equal to m, and in particular where let's say that n is less than or equal to m. So let's take in particular the case where n is less than m is really what I have in mind here. So suppose that Jack has at least 2 sisters, right? At least 2 and at most 4. So, and notice n2 is less than 4 is the case I have in mind. So go ahead and draw a number diagram assuming both of these are true. Well, the at least clause gives you your lower bound, the at most clause gives you your upper bound. Both of them are ruled in as possibilities and anything in between, right? And everything else is excluded, everything else is ruled out. So, law of bivalence, at least, at most, exactly. The law of bivalence bifurcates propositions into the true ones and the false ones, okay? And you might not know for a given proposition which category it falls in, but you've got these 2 classes of propositions, the true ones and the false ones. All right, logic fans, that's it for this one, and we'll see you on the next video.